Alright, hey boys and girls, we are ready to watch a video on the tangent line problem, the major problem that has sparked calculus. So I'm going to do my best to explain it to you. You got questions, be ready to ask because I'll hopefully have the answers. First off, calculus studies the rate of change of functions. That is the major theme of calculus, is the rate of change of functions. The rate of change of functions. So, for example, the slope of a line indicates the rate at which a line rises or falls. So if we think back to algebra, a straight line, a line like this, the slope of that line, so let's say this line is I don't know, 2x plus 5. The slope, which is 2, the 2 is the tells us the rate at which that line changes. Now we know that lines like straight lines like that, the slope goes up 2, right 1, up 2, right 1, up 2, right 1. And for a line, this rate of change, or its slope, is the same at every single point on the line. So straight lines are kind of boring. They go up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1, or down 2, left 1, down 2, left 1, down 2, left 1. So that rate of change is consistent for a point. Well, not all graphs are like that. For all other graphs besides straight lines, the rate at which a graph rises or falls changes from point to point. So again, calculus is the study of the rate of change of functions. How does a function change from point to point? Sorry about that. It was a little, I have no idea what that was. Anyway, how does a line change from point to point? Well, for a straight line, it's pretty boring. It changes the same every single time, and it's just a slope. But for other graphs, that rate of change changes, and that's an important concept to understand. So once again, here I have 4 different graphs for us to check out. And if we look at this first graph, this is a straight line. So what is it? How is it changing from point to point? Well, the graph from point to point is the same, so it goes up and then it goes over, and then it's going to do that same thing again, up and over by the same values. It's pretty boring. A line like this, a parabola, changes. So notice at this particular point right here, at this point right here, the rate of change at that point is pretty steep. It's pretty fast, pretty quick. And then as I get closer to the top here, the rate of change starts to not be so fast, and then at the very top it actually flat lines at that. And then notice as I start to go the other way, at this particular point right here, the rate of change is negative. And again, at this point right here, the rate of change is really negative. It's almost a vertical line. So as I move around a parabola, the rate of change of those points changes. Same thing with a graph like this. Right here, here's the rate of change at this point. It's positive and fairly slow, right? At this point right here, the rate of change is very fast. At this point right here, it's a little bit slower. Over here, it almost flat lines horizontally, so there's the rate of change there. So the whole idea for calculus is studying the rate of change at particular points. And for straight lines, again, it's the same. The slope is the same here as it is here, as it is here. It's pretty boring. But for these other graphs, the rate of change changes. So once again, we see it here. Right here, the slope is very fast, whereas down here, it's a little bit slower, and over here, it's almost completely flat. So it's important that that's the idea of what we're studying in calculus, is the rate of change of a function. Now, to find the rate at which a graph rises or falls at a single point, you could find the slope of the tangent line at that point. If you go back to the 4 graphs I just drew for you, I kept drawing for you the tangent line, the point tangent. So if I'm looking at this graph here, to find the rate at which a graph rises or falls at a single point, so let me pick a point like right here, this point right here. To find the rate at which the graph rises or falls at this point, I need to find the slope of the tangent line at that point. If you guys remember from geometry, a tangent line is a line that comes in and just barely nicks, it barely crosses that point. It might have been the straightest line I've ever drawn in this, by the way. So anyway, the slope of that line would be the rate of change at that point. And notice at this particular point right here, it's going to be a different line. So let me draw that line in here. And again, the tangent line just barely nips it right there. Notice that first off, it's negative. This slope is a negative slope over here. This one right here is positive. And then it changes again, like at this point right here, it's positive again, but a little bit flatter, I guess. If you would even go to say the very, very, very extreme minimum, right, to that relative min, your slope is actually going to be straight horizontal. So the idea is, again, I'm going to try to, you notice I'm repeating a lot of the same concepts here. Calculus is the study of the rate of change of functions. And every point of a function has a different rate of change, except if you're a linear line. Straight lines, it's the same all the time. But if you're a graph like this one, the rate of change at all these points is different. There's a little bit different. It's all about the slope of that tangent line. So this statement down here is a pretty important one. The tangent line to the graph of a function f of x at a particular point, x comma y, is the line that best approximates the slope of the graph at the point. So what we're trying to say is, what is a tangent line? You guys know with circles, right? You learned this back in geometry. Here's a circle, there's the tangent line, the line that just barely nips it. Well, the idea of tangent lines of a function, the tangent line to the graph of a function is at a particular point is the line that best approximates the slope of the graph at that point. Now, what I want to mean by, what are we talking about best? Because this is going to become, what do you mean the best? You mean there's others ones, or there are ones that aren't? Well, let me draw you another graph real quick to explain this. If I have this graph right here, again, just similar to the one, I just don't want to draw on top of that one, and I say, okay, here's this point right here. Well, if I say, Johnny, come and draw the slope, or come and draw the tangent line at that point. Johnny might come in and draw that line right there. And I say, okay, Monica, you're up next. You come and draw the tangent line. She might say, well, I think it's more like here. I think it's like there. And then, I say, Sammy, it's your turn. Sammy, come in. You draw the tangent line. Sammy might say, yeah, I think it's like there. I think that's it right there. The point is, the tangent line is the one that best approximate the slope of the graph at that point. So there could be several different options here. I'm looking for the best one, and you're going to see how that connects here in a second. So we want to find the rate of change between 2 points. So wait a minute, Mr. Frinchek, you said 1 point. I'm talking about 2 points. Well, you're going to see how it all connects here, hopefully. Hopefully I can explain this to you. So if you think about the rate of change between 2 points, so let's say here's point and here's another point, right? If I want to find the rate of change between these 2 points, what I need to do is draw the secant line. Now you're like, what? Tangent lines, secant lines? What is going on here? Relax. Remember from geometry, a secant line is a line that crosses a circle twice. So let me just show you right there, crosses the circle twice. That's a secant line as opposed to a tangent line that just crosses it once. So you'll see where I'm going with this. Just give me a moment. So the rate of change between 2 points would be the slope of this secant line. And that was not a very good straight line I drew. But anyway, so I need to find the slope of that secant line. So now let's remember here how to find slope. Okay, well, slope, if you remember, we use m, right, for slope, and it's the rise over run. So let's see here. If I say that this point right here is x comma y, and here's x right here, right, and over here, right here, here's that y. Now I'm going to slide over and to get to this other point. So now to go from this point to this point, I got to slide over, and I'm going to slide over h. So this would be x plus h. H is some constant, some variable, some constant. So I'm going to slide over a value of h. So that means the distance right here, the distance, the horizontal distance between these 2 points is h, right? So I went from x to x plus h, so I slid over h units, right? That's the run. Well, when you're dealing with run, slope that's on the bottom, right? Slope. Now on the top would be the distance from this point right here, right, to this point right here, the vertical distance right here. That would be the rise, the vertical distance. Well, this vertical distance was y, and another way of saying y is f of x, right? It's another way of saying y. So this point right here is x comma f of x, because y is just another way of saying f of x. So that would be right here, right? Well, this point right here would have a height of f of x plus h, right? Because here was x. So its corresponding y would be f of x. This point right here is x plus h, because I just slid it over h units, so it would be f of x plus h. So the slope would be the y coordinate of the second point, which is x plus h, minus the y coordinate of the other coordinate, f of x. So we got f of x plus h minus f of x all divided by h. So I don't want to confuse anybody, so I'm going to go through that one more time. Okay, and I'm going to use yellow. Hopefully you can see this yellow. Okay, so one more time. We got a point right here. That point is x comma y, and think of that as x comma f of x. So here's the x underneath it. Here's the f of x, right? Same thing as y next to it. Now here's another point. Now that point is just the same point, but I just slid it over x plus h, right? So that gives me a horizontal distance here of h. And then I'm going to have a vertical distance here. That vertical distance is the difference between f of x and this point right here, f of x plus h, right? So I started out here, I went over h. So my horizontal distance, the numerator or the denominator, is h, the run of this line. And then to find the distance, the vertical distance, I got to take the f of x plus h minus the f of x, right? That's the difference in between the two y's. So this is the slope of the secant line. And again, it's f of x, I'm just writing it a little bit bigger here, f of x plus h minus f of x all divided by h. Now, that should look familiar to you, right? We call that the difference quotient. We've called that before. We've been seeing that in class recently. Now, here's the rub. Here's where it all comes together, and this is what's going to drive everything here. Okay, now, we want to find the tangent line, because calculus is not about the rate of change between 2 points. No, it is not. It is about the rate of change between at one point, right? So I want to find the rate of change at this one point right here, this point right here, not the rate of change between 2 points. So it all starts with the secant line. Now, if I come in here and instead of choosing this point, I choose this one, that's going to create this secant line. It's a little bit closer to the tangent line, right? Here's this point right here. I'm going to move in closer. That's going to create this line. And move in a little bit closer. It's going to create this line. Move in a little bit closer. It's going to create this line. And the whole point is as I get closer and closer to the point, I'm going to get closer and closer to the tangent line. Now, I need to slide way over here for a second because I want to draw a little bit of a cleaner picture so you guys can understand this. Okay, once again, here's my parabola, right? Okay, I need a point. There's a point, and I want to find the tangent line at that point. Well, in order to find the best tangent line, I'm going to start by thinking about this secant line here. And then if I move this point in a little bit closer, now that secant line is a little bit closer to the tangent line. Move that point in closer, it's a little bit closer to the tangent line. Move it in closer, it's a little bit closer to the tangent line. They're still secants because they cross twice, but they're getting closer to the tangent line. Get in really, really, really close, and I'm really close to that tangent line. So once I am so close to that point, I might as well be on top of that point, I create the tangent line. So let's think about this. Here is the slope of that secant line, f of x plus h minus f of x, all divided by the horizontal distance h. That's the slope of that secant line. As this limit, as this slope gets closer and closer and closer to 0, as the h value, as the difference between my x and my second point, right? The second point is x plus h. As the distance in between there gets closer and closer to 0, meaning my 2 points are getting closer and closer together, I will get closer and closer to my tangent line. So the limit of the difference quotient. The limit of the slope of that secant line as h approaches 0 is the slope of the tangent line. This is the slope of the tangent line. Calculus is all about finding the slope of the tangent line. It all starts with that secant line. And as those 2 points get closer and closer together, so the distance in between them, h, gets smaller and smaller and smaller, I get closer and closer to that tangent line. So now it all comes together as to why we're finding the limit of the difference quotient. Let's do a problem. Find the slope of a graph, f of x equals x squared, at negative 2 comma 4. So I'm going to briefly draw a picture of this so we can understand this. Here's a rough graph of x squared, parabola. At negative 2 comma 4, negative 2 comma 4 is somewhere over here, somewhere over here. I want to find the slope of that tangent line right there. Well, to do that, I have to find the limit of the difference quotient. I have to find the limit as h approaches 0 of f of x plus h minus f of x all divided by h. This will give me the equation to that slope of the tangent line. Watch how awesome this is going to work. I made this an easy one to start. Okay, now first off I got to plug x plus h in there instead of x squared. That's going to be x plus h squared minus x squared, the function, all divided by h. I will be done solving this limit the moment I can get that h on the bottom to cancel. X squared plus 2xh plus h squared minus x squared. All I did was multiply out that top. The x squareds cancel. I get the limit as h approaches 0 of 2xh plus h squared all divided by h. Factor out the limits here. And again, you got to always write this limit. I know you guys hate it, but you got to do it. Factor out the h on top. I get 2x plus h all divided by h. The h's cancel. Now it's time to find the limit. Now I got those h's to cancel. Right now I can go ahead and plug in 0 for h, and once I plug in 0 for h, I get 2x. Boom, boom, boom. 2x right here. This is a formula for the slope of the tangent line. Here's my function. By finding this limit right here, I am finding a formula for the slope of the tangent line. So now, what is the slope of this tangent line at negative 2 comma 4? Well, the formula is 2 times x. According to this point, x is negative 2. So negative 2 times 2 is negative 4. So the slope of this tangent line, the slope of that tangent line is negative 4. If I wanted to talk about another point, maybe I want to talk about this point, I don't know, let's extend this up. Maybe I want to talk about some point way over here that's at 5 comma 25. What is the slope of that line? Notice it should be positive now, so let's find out. If I plug in 5 into this formula right here for the slope of the tangent line, I get a slope of 10. So at 5, the slope of that tangent line is 10. At negative 2 comma 4, the slope of that tangent line is negative 4. Like I said, the slope, the line, changes from point to point. Let's do another one. Find the slope of the line at f of x equals 3x squared plus 5 at these 2 points. Well, I have to use my difference quotient formula to find a formula for that slope. That's what this is doing. The limit as h approaches 0 of f of x plus h, that's 3 times x plus h squared plus 5, minus the function, so minus 3x squared minus 5. All divided by h. Once again, what am I doing? I'm finding the slope of 2 points. And as those 2 points get closer and closer together, as the difference between them, h, becomes 0, I'm going to get the slope of the tangent line. This is awesome, isn't it? So let's find that formula. Let's see here. So I get 3x squared plus 6xh plus 3h squared minus 3x squared minus 5. If you don't know how I did that, all I did was I did x plus h squared and then distributed to 3. Not that difficult. 3x squareds cancel. I forgot the plus 5. Sorry guys. 3x squared plus 6xh plus 3h squared plus 5 should be in there. So the negative 5 and plus 5 cancel. So I get the limit as h approaches 0 of 6xh plus 3h squared, all divided by h. Now I'm going to do the limit as h approaches 0. Factor out that h. I get 6x plus 3h, all divided by h. The h's cancel. The moment those h's cancel, I'm good to go. Plug in 0 for h, and you get 6x. There is my formula. By the way, 3 times 0, 0. That's why the 3h is gone, because I plugged in 0 for h. 6x, that is my formula for the slope of the tangent line. So now, at this point, what's the slope of the line? Well, the slope of the line is going to be 6x. So that's going to be 6 times negative 4. So the slope at that point is negative 24. So that's a very, very steep negative slope. At this point, the slope is 6x as well, but x is 1/2 at that point. So that's 6 times 1/2. So the slope at that point is a very mediocre 3. I really want this to make sense, guys. I really want everybody to be clear on this. I can't draw this picture enough. I can't have this make more sense. I really want it to make sense to you guys. Here we go. There's my graph. Here's my point. I want to find the slope of this tangent line that goes through that point. But you could draw like a couple different tangent lines. So I want the best tangent line. So I start thinking about the secant lines, right? And as the distance between these 2 points, as the horizontal distance between these 2 points, see, there it was kind of big. Here it was a little bit smaller. Here it's even smaller. Here it's even smaller. As the distance between these points gets closer and closer to 0, I get closer and closer to that true tangent line. And that, my friends, my students, is calculus. Okay? So, the formula for the slope of a graph at a point is right here. This is it. This is a formula for the slope of the tangent line at a graph. That is what we call the formula for the slope of the tangent line at a point x comma y. Now, we have a special name for this. We call it the derivative. This is called the derivative. Now, this is a calculus term, the derivative. We also call it, why is it called the derivative? The derivative, because we derive it from the original function. So we take f of x and we derive a formula for the slope. Now, we have another name for it. We call it the derivative. We also call it f prime. F prime, and we denote it like this, f prime. We literally just put a little hash mark there. I don't know why we do that. That's what we do. Little f prime. F prime is the derivative of a function. So this right here, the limit as h approaches 0 of f of x plus h minus f of x all divided by h is the derivative of a function. We call it f prime, the derivative of a function. And what is the derivative of a function? It is a formula for the slope of the tangent line at a given point. A formula for the slope of a tangent line at a given point. So now I hopefully, hopefully you guys understand the tangent line problem. We will discuss more in class. Peace. Print check out.